We're now looking at some basics to do with the field of logic, obviously pertaining to computer science especially, and logical statements can be evaluated to either true or false. And this is why they're used in computer science, because, or rather computer science has adopted logic in the way it processes data, because true can represent 1 and false can represent 0. Everything in a computer is done in binary with 2 different voltage levels, so logical statements can be implemented in a computer and evaluated. So examples of logical statements are things like the score was 2-1, this is either true or false. 9 is greater than 13, this is false. Age greater than or equal to 17 and the test being passed. You can see we have a connective here, connective and. The individual parts can be evaluated either true or false depending on what the actual variable holds, and then the overall statement can be also evaluated to either true or false. Whereas something like asparagus is tasty is not a logical statement because it's an opinion, it's not a fact, it's not something you can actually evaluate. Before we move on, we need to also talk about truth tables, which are methods of representing every possible output based on inputs to a Boolean expression. So they really show all the combinations. The columns are the inputs and outputs. Q is often used as an output. It doesn't matter. These letters don't matter. It will just be whatever's in your Boolean expression. But essentially they show all the possible inputs, all possible combination of inputs. So the more inputs you have, it gets exponentially more complicated, more combinations arise. And then in the output column you evaluate what the expression would be if the inputs were these values. But this will be clear as you show some examples. But also we're going to be looking at them in terms of zeros and ones, 0 representing false, 1 representing true, but they can also be in terms of T and F, but it's the same thing. So we're going to look at 3 logical operators, the 3 basic ones. There are more, but they're all based on these 3 basic ones. So not is the simplest. This is also called negation, especially in Boolean algebra, which is a slightly more formalised version of what we're looking at. In terms of it being a logic gate, so essentially all these operators are implemented in hardware with logic gates. And this is just a circuit. This is a way of representing a circuit that performs this not operation. Because as I said, everything is done in binary. There needs to be a way of implementing these logical expressions, and they're done through logic gates. So the not operation takes one input and reverses it. Very simple. And this is what the truth table looks like. Only one input, which is A in this case, and Q is our output. So it takes an input. It's either going to be 1 or 0. So firstly, if it's a 0, it makes it into a 1. If it's a 1, it makes it into a 0. And this table defines the not operation. So you'd write it like not A equals Q, but you also can write it with, I forget what this is called, but this is the not symbol. This is symbol of negation, so this just represents not, and you'll see this in Boolean algebra. And also it can be written with a bar on top, so this is A bar equals Q. That's the same as saying not A equals Q. So not's very simple, but make sure you know the 3 different ways you can express it. The second operator is slightly more complicated. This is OR, and it's also called disjunction, so remember that. And it looks a bit like this in terms of a logic gate. Make sure you remember what these logic gates look like. But I didn't really talk about what the not one looked like. So the not one is a triangle with a little circle afterwards. Both consist of the not gate, so they're linked together. So don't leave one out, because it's not a not gate without the circle or the circle and the triangle. So an OR gate disjunction, it's got a curved back and a curved front. This is what it looks like. It's got 2 inputs this time, so A and B. Again, these letters could be anything. It's just the example I'm using. And this returns true, so it returns a 1 if either of the conditions are true, if either of the inputs are true. It will only ever return false if both conditions are false. So as a truth table, it's now a larger truth table because we have to express all the possible combinations. So when they're both 0 and they're both different and when they're both the same. So as you can see in the output column, OR only returns false when both are false. In all other conditions, if there's a 1 in one of the inputs, it outputs a 1. So as you might expect, it's written A or B equals Q. Also written with a little V here, which just means or disjunction. And also can be written with a plus, because what you're kind of doing here, you're kind of adding them together. So 0 plus 0 is 0, 0 plus 1 is 1, and the only exception being here, where 1 plus 1 is clearly not 1, but we're only dealing with 2 values here, so that's one way of thinking about it. But essentially OR only returns false if both inputs are false. The final operator we're looking at is AND. This is also called conjunction, and this is got a flat back and a curved front, again 2 inputs. This returns true if both conditions are true, otherwise the result is false. So it can only return true if both inputs are true. So the truth table shows that you're only ever going to get a 1 as your output if both inputs are 1. In all other cases, a 0 is returned because both inputs aren't 1. And this is written as A and B equals Q, and also the opposite of the OR operator, so this is an upside down V, A conjunction B equals Q, and also it can be written as a dot. This is representing multiplication because again it's kind of like, it is in this case 0 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. So this also can be seen as multiplication, which is why a little dot is used. This is often used as shorthand in maths to represent multiplication. Here's all the information again if you want to have a little pause and see the differences between all 3 of them. So these operations are just relatively kind of abstract, used in other fields as well, so discrete maths, linguistics, philosophy, and the logic gates are actually representing an implementation in hardware, so as a digital circuit of these operations. So these are more used by computer scientists obviously, but also electrical engineers, and these symbols are used in larger diagrams to represent more complicated circuits that make use of these basic building blocks. So these are just implementations, or representing, I should say, implementations of these logical operations.